Thank you very much. So this talk is a kind of a bridge between optimization of distances, minimization of distances between vector and a set of vector, or probability vector and a set of probability vectors, and large deviation theory. So we start, the global context is minimization of distances. Those distances would be either Caesar type distances or more globally Bregman type distances. I briefly recall a few notation. So generator will be a positive function, convex, etc. You know the context. And here is we will restrict to situations where we consider distances between vectors with k components. So we work in, for example, for probability measures in the simplex of Rk. Okay, this will be much simpler, and it will provide explicit solutions for various problems. So we're interested in this kind of problems. We consider a set omega in Rk or in Sk, the simplex, according to the context, and we want to minimize divergence here between Q and P. P is the reference measure. Q runs in omega. And omega will be a non-void subset in Rk with some regularity property, but we will not impose convexity, for example. And the talk focuses on methods of type Monte Carlo type for the minimization of those kinds of objects. In other contexts, which we will not deal explicitly, but I will give references on that, we will consider Bregman type divergences and look at the minimum value of Bregman divergences always on subsets of vectors. And those Bregman divergences will be induced by modification of basic divergence generator phi. From this global setting, we can recover what happens in the classical Caesar type divergences or the classical Bregman ones. Okay, so but I will stick on the Caesar framework, which is more at hand. Okay, so we consider sets omega on which we were about to make optimization, and with difference with parametric statistics or parametric minimization problems, we will consider that omega has non-void interior in Rk at the moment. And this condition is simply a condition of regularity. Say, for example, if omega is an open set, it will be satisfied, but it's only done in order that in all coming limiting properties, we will not have a limit sup and a limit inf according to the geometry of the set omega. So we will say that functional phi is minimizable on omega if we are able to build up a kind of framework for which the infimum will result as a limit of quantities of this kind. That means that we will be able to construct sequences of random elements xn such that according to the measure Pn, we will have this statement. That means that if we are able to construct explicitly such sequences xn, then by Monte Carlo type of methods, in order to simulate those xn, we will be able to evaluate the probability that xn belongs to omega through counting, because we will have realizations of xn. And so we will have approximation of the infimum value of the functional only by counting. So we substitute a minimization or an optimization problem by a counting problem. So this is basically the setting, and the point is to build the adequate sequence xn, which therefore belong to the same space as omega does, in such a way that the occurrence of xn in omega will be in full correspondence with the minimization of the function phi. So clearly the function, the sequence xn or random variables will be dependent upon the choice of p, obviously, and necessarily function also of the basic divergence function of generator of the divergence phi. So it was no surprise that the construction of the sequence xn makes those elements appear quite natural. Okay, so we have two contexts. The first one is a context deterministic optimization problems, and this slide is only to say that up to a normalization we can suppose that all entries of P firstly are positive, and secondly add to 1. So the context is that P will be a probability vector with non-null components in Rk on points 1 to k. In the statistical context, P will not be known. At the end, what we would like to do is to infer some knowledge on the inference, on the infimum of phi of qp when q belongs to omega. But P is unknown and is unknown only through sampling. This is the case for statisticians. In that case, we would like to investigate the infimum value of the criterion phi based on Pn when q runs in omega, and this will be a way to quantify the adequacy of, obviously, P to omega. And this is the main tool for assessing the fact that we make model choice. So for the statistician point of view, this has to do with model choice. Okay, I have to give just one basic point is the following. When the generator, which is a convex function with phi of 1 equals 0, has a special structure, then we are able to build up the sequence xn I talked about previously. That means to get the corresponding approximating scheme in order to have the minimum, the infimum procedure. And the setting is the following. When phi allows for the up here, this characterization, that means that when phi is the Legendre transform of the cumulant function for some random variable w, then it happens, for reasons we will see just now, that we are able to build up this sequence xn. So what does that mean? That means that we introduce a random variable w, and we assume that phi is the Legendre transform of lambda, which is the log of this quantity. We will see many examples for which this holds, and basically it holds for nearly all common generators. So phi of t here is our basic assumptions, and we will focus attention at the end of the talk on the sufficient conditions and tools for assessing the existence indeed of such random variable w that will be instrumental in order to proceed to the minimization procedure. I start in order to give some insight on the very classical Kramer result on large deviation, saying that if phi is indeed the Legendre transform of the cumulant generating function of the w's, then we have the fact that the empirical distribution, the empirical mean of the w's satisfies a large deviation result, meaning the following. The probability that the empirical mean belongs to omega can be approximated by exponential minus n times the infimum. this is the basic large deviation result on k points. Here for empirical means having light tails, say. So this is our first point. Remember that phi of p writes down, phi p of q writes down in this form. So we will build a bridge between Cramer's theorem and the minimization of phi p of q when q belongs to omega, starting from there. And the construction is as follows. So the basic setting is that p is given as a vector in Rk, and we want to minimize that. So how we do that? If we have a phi function, we first should assume that this phi function can be seen as a rate function for large deviation. And this means to build a correspondence between phi and a probability measured zeta, which is the law of W's, and this is what we will do presently. And now we will build up, here is a p, pn, and p here, probability space for building the sequence xn. And this is done in the following way. We build up xn, of which the counting in omega will result as a way to minimize phi, the divergence, as a point in Rk, and it will be indeed a kind of an empirical, say, means, okay, made by blocks. The cardinality of this block is related to p, so p appears here in the number of replications of the wi's in the block. So this vector xn indeed is built upon p, because p is inherent in the construction of the blocks. The distribution of the w's is linked to phi, the generator, because the generator is supposed to be the rate deviation according to the distribution w. So we take the xn, and what we have as a first result is, given a regular set omega in this sense, we have this limit property, which is the clue for our optimization method. So we see that the infimum of the functional on omega can be written as a limit of, say, the frequencies of the xn that fall in combien?
13 minutes.
Déjà 13? Wow. Bon, okay. So we simulate trends, and what we get is the xn, and we just count. Details are in here. Okay, when we go to the case when we want to optimize in a statistical context, then omega is in the simplex. We have to renormalize the w, the vector xn, which is done in here. So we renormalize by the sum. So this adds to 1, say, typically. So we're in the simplex, basically. And we have the following large deviation result. And what is important is that what we want is the infimum of phi of p on q, not on infimum of m. But in many cases, we're able to express the minimum of an m as a function of phi of p q itself. And then we're able to make an inversion and go back to the previous problem. So this is written on here, and this is typically the case for power divergences. Okay, here is an explicit example on how we can do that. Here is an example for the power divergences of the various laws of the W's. Gamma is the index of the power divergence. And here, this slide states the variability, the versatility of the laws of the W's according to the exponent of the divergence. The divergence can be Hellinger, can be chi-square, etc., and this makes quite a lot of difference in the distribution of the W's. This has been noticed in another context by Le Tac and others on natural exponential families, because it's very linked to the same kind of problems. Here are a few examples. I'll go very quickly on that. You see, according to the various divergences, we get explicit forms for the wave. Just one thing to finish. How can we identify the condition that stated that the generator is indeed a rate function for some random variable W? And here is a number of items stating that in some cases when we are given phi, the idea is the following. Phi should be the Legendre transform of a Laplace of the moment generating function. So we know that a moment generating function corresponds indeed to a random variable under some circumstances. This is known as Bernstein or Wieder type theorems on integral transforms that can be expressed as integrals with respect to probability measures. So this is one way to identify, given phi, taking the Legendre and identifying the result through Wieder or Bernstein theorem. And, but this is quite an open problem since the 30s, indeed, as such. So what we have simply defined is a kind of a tool which is much easier somehow. It is not obviously a complete solution to this identification problem, but it has very much to do with it. So we take a function f, and from it we infer what should be the moment generating function and what should be the divergence. And then we can turn around and play around those three things, either starting from an f function, either starting from a phi divergence, either going from an f function, so we can take basic f functions pertaining to classical cases and turn around and modify them. For example, if we start from the f function that has to do with divergences, we can, for example, that one, we can simply modify them and turn to define the generators associated to it. So we have a kind of an interplay around these theorems that avoid somehow a catalog connected with Wieder or Bernstein theorem. For example, for robust divergences, that means that we would like the generator such that its derivative would be bounded. So we are also able to build up the f function. The f function is just instrumental. It's this function. And then from here we can go to lambda and then identify. And for example, if we want to go to robust divergences and minimization of robust divergences, we first can use our trick with simulation to get the minimizers, but above all, we can build up the W's, and the W's for robust divergences would be, for example, distributed as asymmetric Laplace, etc. This is in the best thing is about the references. Here is an extended paper, long paper, with many result cases, which has been published in IEEE. There is something in relation, a very extended study on Varadhan's lemma and applications of those methods through Varadhan's lemma for global optimization problems that will be on archive just now. Few notions of the F trick is in the GSI present, etc. And this goes down also to various interesting papers by César Gamboa-Garcia or Lise Vajda, etc. So thank you very much for attention. Thank you.